Hello, this is Jacob Powers, and this is my material science project on T700 raw carbon fiber and pickleball paddle construction. In pickleball, a paddle's performance is heavily influenced by the material used in construction. In this project, I'll be exploring how specific material properties like elasticity, dampening, and stiffness impact real gameplay factors such as power and bounce on the paddle. For this study, I'm focusing specifically on surface materials. Common materials used in construction of the surface on a pickleball paddle are graphite, Kevlar, fiberglass, wood, and carbon fiber. The main material that I'm focusing on in this project is T700 raw carbon fiber. It's becoming the most common material used in paddle faces due to its high performance in bounce and having a lot of grip on the ball. T700 raw carbon is a high-strength standard modulus material developed by Toray Industries. It's made by processing PAN fibers, which is polyacrylonitrile, through a sequence of oxidation, carbonization, and surface treatment, followed by coating the fibers with epoxy-compatible sizing. T700 has a tensile strength of about 4.9 gigapascals and a modulus of around 230 gigapascals, meaning it's both very strong and stiff, but it's not too stiff where it becomes brittle, similar to T800 and T1000, which are very expensive and very fragile materials, making them not great for pickleball paddles. Another key advantage of T700 is its woven 3K sheets. These uncoated surfaces offer natural grit without needing additional resin, paint, or sandpaper layers. This is especially valuable in pickleball, where textured paddle face enhances spin performance and longevity. The image on the right shows the composite makeup of how the layers or plies are arranged to form a strong and balanced paddle face. At the very top and bottom, we have woven carbon fiber layers in a 2x2 twill pattern. These woven layers serve multiple purposes, such as protecting from damage and creating a textured finish that helps with grip. And between the woven layers, we have alternating unidirectional carbon fiber layers, which are fibers all aligned in a single direction, and then the layup alternates between 0 and 90 degrees, meaning that the fiber direction shifts between horizontal and vertical from one layer to the next. This alternating pattern is critical because it gives the paddle multi-directional strength. It can resist forces coming from different angles without warping or breaking. And the unidirectional layer provides the bulk of the stiffness and load-bearing strength, while the outer woven layers enhance surface toughness and spin. The goal of my experiment for my project is to test and compare the bounce of a pickleball on a T700 carbon fiber paddle and compare it to other materials. And I was going to do this by just demonstrating the principles of elasticity and bounce with the coefficient of restitution. Setting up my experiment, I used two vice clamps attached to a table. One was holding a paddle that was facing the ceiling, the other held a ruler vertically next to the paddle. I had a phone mounted facing the setup of the two mounts to record in slow motion, and then I would drop a ball from 20 inches up on the ruler down to the paddle surface, and I would measure the heights of the bounce and keep the 5 highest bounces and take the average for each paddle. So this is the setup that I used. These are the two clamps holding the paddle and the ruler. This is the phone mount that would record. The post-it note on the ruler is marking the 30-inch mark where I dropped the bottom of the ball. So I would line up the ball with the post-it note, drop it down to the paddle, which was marked at the 10-inch mark. So the distance between the surface of the paddle and the post-it note would be 20 inches. And I would simply record the same ball being dropped 5 times on the same paddle and take the average height as the bounce height. Here's a demonstration of what the experiment looked like. After recording the 5 trials on each paddle, I took the videos, uploaded them to Tracker, a software measurement that I could use to do a frame by frame to calculate the bounce height of the ball. So I would create a scale using the ruler in the video, and then I would find where the ball stopped onto the paddle, and then where it peaked after hitting the paddle, where it would be the maximum height. I would freeze the frame and mark both points, and then I would use the ruler provided by the software to measure the bounce height the ball got. The coefficient of restitution, or core, measures how much kinetic energy is conserved in a collision. A higher core means the object bounces back more, indicating better energy return. In this case, that bounce behavior is influenced by the paddle face material. Core is directly affected by a material's elasticity, which we quantify using Young's modulus. This tells us how stiff a material is or how much it resists deformation when force is applied. Materials with a high Young's modulus, like carbon fiber and aluminum, are stiffer and deform less during impact because they store and release energy more efficiently. They often result in a higher core value. On the other hand, materials with lower stiffness like polypropylene, Nomex, or wood deform more and tend to absorb more of the ball's energy. This is due to dampening, which is the material's ability to dissipate energy internally, in this case often as vibrations, rather than returning it to the ball. So based on the table shown in the slide, the materials with a higher modulus, like carbon fiber, fiberglass, graphite, should have much higher bounce heights or core numbers compared to those of polypropylenes or wood. So this is the results from my experiment. Core, or the coefficient of restitution, was calculated by the square root of the height of the bounce divided by the height of the initial ball. In this case, the height initially was 20 inches, and the height of the bounce was calculated using the Tracker measuring tool. Overall, the T700 material paddles did the best, with the highest score coming from the Ripple paddle that was made of T700, and the second place was actually from an 18K 3D carbon fiber paddle that was not T700. And in last place, of course, based on its Young's model, was the wood paddle active, which had a core of less than 5. It had a maximum height of less than 5 and a core of less than 0.5. So in conclusion from the results, the T700 raw carbon fibers seemed to have the highest core value, indicating it had superior energy return and performance, and this aligned with materials that have a higher Young modulus like carbon fiber and graphite will result in higher bounce heights.